Greetings, the Astro 30 here yet again, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and subscribing if you haven't done so already. Cheers. Today I'm going to be looking at a circuit that Tony Rogers sent me, one of my subscribers. It's a DC speaker protector circuit. There's nothing really that special about it, but it is intriguing. And the intriguing part is how we're doing the DC detection, which is down here. It's using a bridge rectifier and a single transistor to detect both the positive and the negative going cycles. Now, because a bridge rectifier will correct or rectify whatever polarity is here compared to ground, so say this was negative compared to ground, well, it will rectify it so the positive will always be here on the two cathodes and the negative portion will always be here on the two anodes. And the reverse is true. If this was positive with respect to ground, well, it would still rectify positive out the cathodes here to the base of the transistor and the negative on the anodes of the bridge rectifier here to the emitter. So what this is effectively doing is it's going to be bringing up a negative voltage potential to the base of this transistor here, Q3, which is part of the Darlington driver for the two relays over here. We also have a turn-on delay, which is just simply coming off of the transformer secondary through this 1N4148 diode, 150k series resistor, and this 220 microfarad capacitor to ground. So that forms a RC delay for the base of this transistor. So it gives a slow turn on to this transistor. And once this transistor reaches about 0.6 of a volt, it'll conduct. So will the output transistor here, Q4, which is a 2SD669, which is a TO126 device. So in my case, I could probably get away with a BD139 here for testing. And then it will turn the relay on by bringing ground up into the relays and across from the positive rail, which is also taken off through this diode here, off of the transformer secondary, this 1M4004, this 220 microfarad smoothing capacitor, and then it gets clamped down with R1 and ZD1 to 24 volts, and then that powers the rest of the circuit. These two transistors here form a multi-vibrator or flip-flop, so that when the relays aren't engaged, well, this LED will flash at a certain rate, which is determined by these two capacitors and the resistors, etc. Once Q3's base reaches 0.63 of a volt and starts to conduct, well, ground is also brought up through this second 1N4148 diode, which then gives a path for the LED directly between the collector here to ground so that the LED stays illuminated all the time, effectively taking the flashing circuit out of circuit, basically. And finally, we have a 75 to 100 degrees C or Celsius thermal switch, which is normally closed. And all that does is when it gets to a certain temperature, 75 degrees say, it'll open and therefore remove the current drive to the relays and they drop out. But of course the rest of the circuit will still have power, and this LED will not flash when this is disconnected because this driver circuitry is still allowing ground up to the LED so that there's a current flow for it. And we've just got a HQG point, which basically stands for high quality ground point, to the speaker's common. So this HQ ground point, you would take it basically off of the star ground of the amplifier chassis, for instance. Now this circuit was designed by a guy named Randy Sloan from the Audiophile Construction Manual. Not sure when. I really hate that term, audiophile. It sounds predatory. And they also come out with the most outlandish claims to do with audio, such as gold-plated connectors improved the sound, with no scientific evidence to back that up. So in some respects, audiophiles can be kind of annoying. That's just my own opinion on it. So if you're an audiophile, good for you. So the other design aspect he's got going on here is these two back-to-back 330 microfarad capacitors. Now what this is essentially doing is because a capacitor, especially a polarized electrolytic, does not like being charged in the reverse direction. So take for instance we have the negative portion of the DC offset going across this capacitor and ground. Well, that's reverse charging the capacitor, assuming C5 wasn't there. So what we do is we put these back to back with the two positives going together, and each negative, one side goes to the input circuitry and the other side goes to ground. We've got a bipolar capacitor. Its total value would be around 115 microfarad because capacitors in series divide. However, that's old school way of doing it. We now use bipolar capacitors, but the disadvantage to them are they're only rated at around about 50 volt, most of them. So unless you can find a specially designed one with a higher voltage rating, putting two 63 volt 330 microfarad capacitors in series like this, back to back, would essentially give you a total voltage working of the entire thing of 126 volts. So there is that. So what I'm going to do is I'm going to build this up in stages, and I'll probably start with this shunt regulator thing. I'm going to be using a 12 volt relay for the test because I don't have a 24 volt one. And I'm going to set this to a 12 volt Zener instead of the 24 volt, which may affect the flash rate of this multivibrator. But I'm going to build this part up first and the multivibrator, see what the flash rate of the LED is, etc. Then I'll build up this part of the circuit, which is the delay constant part, then the drivers to a relay, and then this diode in here as well to see if the LED remains solid when the relay engages. And then I'll worry about this DC input detection circuitry. So I'm going to start breadboarding this out and have a bit of fun. So let's get going. And a short time later, only about 20 minutes, I've got the multivibrator circuit built up, indication LED, the AC rectifying part of the circuit. I'm only using a 25 volt 220 here, so I have to keep the voltage low. So this is not really going to be tested on a mains transformer or anything like that. I mean, I could, but it'd have to be no more than 15 volts on the secondary. Got the clamping circuitry up here. I'm using a 470 ohm 1 watt device. It really needs to be more than that, like a 2 to 5 watt device, but for what I'm doing here, it should be enough just to test the concept of the circuit. Now, I've also got a 1N4148 diode in here going to the collector of the second transistor of the multivibrator, and this fly wire connected to its cathode, which I can bring to ground, which is on this green part of the circuit here, just to test whether the LED remains solid, etc. So I've got my power supply set to around about 19.3 volts, and we should have like close to 12 volts after the clamping circuit, which is on this rail here. So I'll turn the circuit on. Well, we can see the LED is flashing. Probably a little bit fast for my liking. It's like 1.5 hertz or something. But if I bring the cathode of that signal diode to ground, the LED comes on and remains solid. And release it as if the relays have just dropped out. There you go. So that part of the circuit is working. Well, I kind of expected it to, because it's a simple circuit. There's nothing really spectacular about it. So I'm just going to do a voltage measurement on the clamping circuit once I untangle my multimeter leads, and we'll see what sort of voltage we get. So I have to come around the camera. So at the cathode of the Zener, we've got about 11.87 volts, as we can see there, which is wunderbar. And if I actually bring that cathode of that diode to ground again, voltage drops off a little, not by much, and then we'll come back up once I release the lead from ground. Okay, so now it'd be a good idea to build the driver circuitry to the relay, see if that will work, which it should. That's a 600 millicandela LED, by the way. Yeah, I'm also using BC546s here instead of the 2N555s because I don't have any. Essentially, here in the multivibrator, you could get away with BC547 or even 2N3904. It doesn't really matter. It's only a low current, low power part of the circuit here. For the driver, the first part of the Darlington, I'm going to use a BC546, and the other part of the Darlington, the power side of it, I'm going to use a BD139. And it's only using a power transistor on the driving side of the circuit because we are going to be driving two relays. So a Darlington with a power transistor, probably mounted on a heatsink, would be a good idea to drive the relays, so it had the circuit, the Darlington pair, have enough gain to drive two relays, is what I'm trying to say. A single transistor on its own doesn't have enough gain. So let me get to building that and we'll come back with some test results. Well, I've got the driver circuitry in, and it took a lot of messing around to get the thing to actually work. I had no delay at first, but that's because I was using a 47 ohm resistor instead of 150k. I don't know why that happened. And I was also using a BC556 as the driver to the Darlington stage there, which is completely wrong. And well, I've been messing about with it now for about an hour. I have got it to work as a delay, but I cannot get the LED circuitry off of the collector of the driver through the cathode of the signal diode to actually shut the LED off. It just refuses to do so. Well, it will shut off, but I can never get the relay to re-engage again because it's too much current probably going through the LED itself to the transistor. I don't know. So I'll turn it on. And the relay went click, so there is a delay there. If I connect this flying wire which goes to the cathode of that diode to the collector, well, it is on solid, but it is pulsing. Now, it could be the resistance of my relay coil too. It's supposed to be around 600 ohms. This is only like 300 and something, I think it is. Turn it off. Relay goes out. Turn it back on. Well, the LED will go out, but the relay never comes back on. And in fact, with the relay disconnected, that LED stops pulsing. Yeah, that's a pain in the ass. I don't know how I'm going to correct that either. But what I do want to know is, will this drive two relays at the same time? So I will put my fly wires, when I can find what I did with the other one, which is knocking about somewhere. Here's one. And I'll connect that to a second relay, which I just happen to handily have up here. So polarity does not matter. Well, that relay didn't come on. No. No, it can't. Bummer. The circuit will not drive two relays. I need to find out why. So maybe because the voltage now has dropped too low. Let's now measure across the positive rail. Oh yeah, well, it's dropped down to 5 volts now. That'd probably be why. And the 470 ohm is getting quite warm. Okay. I might set up a series pass regulator up here just to help with current. See if that makes a difference. Couldn't hurt. Okay, I've got another TIP 41C here as a series pass element. And yes, now both relays do come on, because if I measure at our positive rail point, we've now got 11 point, well, around about 11 volts there, which is much better. And both relays are energized. which is good. So that's fine. That is starting to warm up. So I may want to attach a heatsink to that before I go any further. But what I want to see is, does this now still operate? Now the circuit works. Isn't that special? Right, so the issue was there's not enough current in that Zener diode to provide the rest of the circuit the correct voltage, which is understandable. The Zener diode on its own is only really good up to about 60 mA of current draw, and I was trying to draw about 70, and yeah, it doesn't seem to like it. So I will attach a heatsink to that transistor to help with dissipation of heat, just so I don't destroy the thing. That's the last thing I want to do. I did have a heatsink somewhere, I saw it, there it is. So I'll connect up one of these for testing, and there's a screw around somewhere, I think, and I'll continue on with the next part. But I've got to get a move on because I've got other things to do today. So I just wanted to get the preliminary stuff working, which it seems to, but at the same time I had to make a modification to the circuit to make it work. So yeah, originally maybe if it was running off of a higher power supply, it probably would have worked okay. But let me attach this heatsink and we'll continue on. So here's what I got. The heatsink is now attached to the tip 41, and it is getting slightly warm. But I have to remember that this is going to be dealing with ripple current because it's going to be connected to a transformer, so this will probably get a lot more hotter. So it needs at least some form of decent heat sinking. I've also changed out the 470 ohm, well, which is now a base resistor, to a 2K2 half watt, which is not much happening to it, because 470 ohm is too low and it's driving the base a little bit too hard. So we don't need to do that. And with the circuit powered up, I'll measure the 12 volt rail, and we've got 10.99 volt DC there, which is perfectly fine. I bet that if I remove one relay, it will jump up a little. So that's perfectly fine. I went back to the BD139 as the driver transistor. It seems to be functioning fine now. It doesn't need to be a TIP 41C. It doesn't also appear to be needing heat sinking. It's barely getting warm. So that's good. The LED is not pulsating like it was before either, so that's great. With the iris turned right down, I can see it's slightly pulsating, but to the naked eye, it is pulsating a little. Unless you're going to stare at it, you're not going to notice. I could try a lower intensity LED as well, just to see if it's more noticeable with a higher brightness. Yeah, I can really see it flickering a bit there with even that LED. It is functioning though, so I'm going to say that it is working as well as it can, I guess. So I guess the next step will be to include the detection circuitry. I'm going to have to build my own bridge rectifier for this because I don't have a suitable bridge rectifier. I'm assuming you can just use a W04 type button bridge rectifier for this, because we're not dealing with a lot of current, we're just mainly dealing with voltage, so it needs to at least be like, 400 volt diodes. So I'll make them up out of 1N 4004s and a couple of 10k resistors there, and see if we can make the DC detection circuitry work. But I've got to do that a little bit later because I have to start getting ready to go to work, unfortunately. So it'll only be a few seconds for you, probably tomorrow for me. So yeah, I'll be back tomorrow and I'll concentrate on this part of the circuit. Alright, see you tomorrow. So I want to make a full bridge rectifier, and I can, using 4 diodes, like everyone's been doing for years. Well, good morning. It's the next day. It's only about 7 o'clock in the morning, and I only used that electro boom reference there because I found it funny, mainly because that's the incorrect name for it. It's actually a full wave bridge rectifier, or just a full wave bridge, not a full bridge rectifier. Anyway, there's the DC detection circuitry up there, consisting of a BC546 transistor, 4 diodes forming the full bridge rectifier, full wave bridge rectifier, and 2 330 microfarad 25 volt caps in this case, back to back with the positive plates connected together, as per the schematic, I think. Or did I get that the wrong way round? I may have got the polarity of that round the wrong way. No, it is the correct way round. For all intents and purposes, it doesn't really matter which way round you put it, whether the negative plates are together or the positive plates are together. It's still going to do the same thing. Anyway, I've got a second DC supply, which is currently set at 17.8. One side of it's connected to the ground of the circuit because it needs a ground reference of the other supply, otherwise it's not going to work. And this is just the positive of that supply. The input point is here. So I'll touch the pin with the positive probe. Very quick to react, but it's very slow to reset. That's the only problem. Now, the reason for that is these capacitors now have to discharge, and that takes time. So what probably would be a good idea is if we put, say, a bleed resistor across those capacitors, in this case a 22K, which there probably should be a bleed resistor there to help it, there it goes, reset faster. So I'll do that by moving that wire down there, and I'll put this resistor across ground and the positive point of the capacitor's input, and we'll test again. Take my probe, and it resets faster. So now I'll switch the polarity around. So now we're looking at negative DC. Still reacts. In fact, in the negative direction it seems to be slower to reset, but I might have had it on there too long. Yeah. Alright. I think it's also slower to react. I have put captions down below of the time it took for me touching the probe to the input for the relays to drop out. So that will give you how many milliseconds that took. But yeah, it's working. It just seems to be in the negative direction it takes longer to reset than it does in the positive direction, which I find interesting. I'm going to take a few more voltage measurements in a minute. Okay. So anyway, what I want to know is now, when we've got a DC fault at the input here, what our voltage across these capacitors are, and then I want to know what this transistor's voltage is across base and emitter. So what I'll do is I'll hook up a multimeter and we'll have a look. Alright, multimeter's hooked up. Well, the negative probe is anyway. I'll just introduce the DC fault, and now I'll measure it across the capacitor. 1.9 volt. Okay, so yeah, that's all well and good. So I'll just disconnect the DC fault. and it bleeds off really quick. Okay, now to measure at basically the output of the bridge rectifier, which is going to be a little bit more of a challenge to do. Yeah, well, that will work. I've got some clip leads across the emitter and the base, basically the negative and the positive of the bridge rectifier. So I'll just introduce that DC fault condition again. About 0.7 of a volt. Now, if I increase the voltage supply, it does creep up a little, but not by much. So that's good. That means that the base of that transistor is not going to experience that much voltage in its life. Remove the fault. And it drops out around about 0.4 of a volt. Very, very nice. It's a sexy time. No, it's not. Okay. Very good. So the circuit is working as it should. And because of what the voltage across this cap is, we could probably just use a 50 volt bipolar 100 microfarad and be done with it. In fact, because I never did like the idea of having two capacitors back to back anyway, I'll stick in said bipolar capacitor. If I can, so get the bastard to go in the holes. There we go. Still works. And we've still got the same voltage at the base. So now I'm going to disconnect that. Although I should probably measure the voltage at the base with reference to ground, see what the difference is. More like 1.3 volt. Still acceptable. And that will probably be with voltage as well. In fact, I'm down to 10 volts and I only dropped off by about probably 200 millivolt. So yeah, actually, what is the minimum voltage required to make this circuit operate? So I wind the voltage right down to about a volt, right? Circuit went off and reset. We've got 0.456, 1 volt, 1.4 volts, 1.7, 1.8, 2 volts. There we go. I'm going to say about 2 volts. So it requires 2 volts DC at the input for it to react. Or maybe not. Okay, let's increase that a bit more. We're more like 2.7 there. It's a bit slow to react at that low voltage, but yeah, a minimum of about 2.7 and the circuit will react. So I'll put this back up to 3 volts. Still slow to react. But let's face it, an amplifier is going to have a higher supply rail than 3 volts. It's going to be like, you know, anywhere between 35 volt and 60 volt. So the higher the voltage potential, the quicker it's going to react. So I'm going to wind the supply right back up to its maximum of 19.1 in this case. So I'm very happy with how the circuit actually operates. I had made a couple of changes, but I can't really see any other need to modify it any further. And that's barely warm, so all well and good. So what I might do is I might fire up the scope and I'll measure at the multivibrator basically where the LED is, across the LED, to see if we can actually detect on the scope that pulsating from the LED. Yes, well, measuring at the collector of Q2 and ground, that would be a yes. As we can see, there's a pulse there. As to what its frequency is, it's unknown because it's happening so fast and my time base is so slow that the scope cannot get a reading. Oh, there we go. It's more like 2.83 Hertz, which is probably what the flash rate of that LED is. Let me introduce the DC fault so the LED is actually flashing. Okay, so that LED is flashing at around 2 Hertz. That's 2 cycles per second. Might want to drop that voltage the other way, idiot. Like that so we can see it. I still think it's a bit fast for my liking. I like it more like slow on, off, on, off. Now that can be achieved by changing the values of the capacitors in the multi-vibrator circuit here to something like probably like 2.2 microfarad. So anyway, I'll get rid of the DC fault. And as we can see, well, there is a blip on the scope there. So even visually you can sort of see it if you stare at the LED really closely. But it's definitely picked up on the camera with the iris turned down. As you can see there, it's out of focus because, well, I had to zoom in a bit, but there was a definite flicker there. I'm not really sure how I would correct that. Or even if I bother. I'm going to leave it like that because I don't really want to try and mess around and redesign the circuit too much. So very good, it's working. And I'm happy about that fact. That's how I'm going to leave it. So I'm going to draw up the schematic now on the whiteboard so we can look at, well, the differences between the original, which are very subtle. So here's my rather badly redrawn schematic. I do apologise for that. It is early in the morning and my hand is not working. So everything from this point of the circuit forwards is the same as the original. Nothing's changed there, except the values of the transistors for the driver. Now, the other change I did make was adding this series pass element, the TIP41C here for our 12 volt rail. The emitter's on this side. I know you can't really see it, but that's where the emitter is. Because this Zener diode on its own just doesn't have the current capability to drive 2 relays at once. It just falls on its face when you start to draw current, and the voltage drops down to about 5 volts as we saw. The other change was changing the back-to-back capacitor arrangement to a 100 microfarad non-polarized. Seems to work. And adding a bleed resistor of 22K to help with discharging that capacitor a little bit quicker. And down here is our full bridge rectifier going into a BC546 as well. One AC connection goes to this network and this one goes to ground. Now the relay contacts are not shown, but each common point of each relay would go to one of these inputs, either the left or the right respectively, and each normally open set of contacts would go out to each speaker. And I haven't shown the high quality ground line because, well, it's not really necessary. But all in all, the circuit works and works really effectively. So, thank you Tony Rogers for sharing that with me. I'm very appreciative. It gave me something to mess around with. So, until next time, happy protecting. It actually literally smells like shit in here now. I'm the Astro 30, and if you enjoyed this video, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, thanks for watching, have a great day.